When the U.S. entered the war in Southeast Asia in the early 1960s, the Air Force was completely unprepared for the type of combat it would face. In the 1950s, the Air Force was built primarily as a nuclear deterrent force. And in Southeast Asia, the Air Force found itself trying to deal with very heavy jungle and counterinsurgency warfare, and at the same time deal with some of the most dangerous and difficult air defenses in the world in the Rolling Thunder campaign in North Vietnam. During this conflict, the Air Force labs played a very important role in helping the Air Force adapt to this very new type of combat. The Southeast Asia War saw the development of the jamming pod, and the Air Force still uses jamming pods today. This example here is an ALQ-71. This was the very first type of jamming pod used by the Air Force. And the work to develop this jamming pod it parallels work done being today in the Sensors Directorate, particularly with the development of the Agile pod, which is far more capable than this very early pod. Now, these were developed because of the threat primarily of the surface-to-air missile, particularly the SA-2 missile, is a Soviet missile used by the North Vietnamese. And basically what this did is it sent out signals that drowned out the scopes of the SA-2 operators in their control vans. And these were so important that there was an order given that no tactical aircraft could go over North Vietnam without carrying at least one jamming pod. Now, another counter to the SA-2 was the development of the Wild Weasel mission. And the first Air Force aircraft was shot down by an SA-2 in July of 1965. And we really needed a solution, or else we would simply not be able to continue missions over North Vietnam. And the Wild Weasels were one of those solutions, and they were born during the Southeast Asia War, and we still have Wild Weasels in the Air Force today. And their job is the suppression of enemy air defenses, or SEAD. And they're basically going after these surface-to-air missile sites. And key to the development of the Wild Weasels was this scope right here, developed by ATI, which was a small business. And this scope detected the signals from the SA-2 and basically gave direction and strength of the SA-2 signals. And with ATI being a small business, this kind of parallels some of the work being done by AFRL today, which really leverages the power of small businesses and startups to help solve Air Force problems. Well, there was a backseat operator who would look at this scope, and this would basically get the crew oriented to where the surface-to-air missile site was, and then they would attack it physically. So this is before the development of anti-radiation missiles. They would just use bombs and unguided rockets. However, the Wild Weasels in the labs developed anti-radiation missiles during the Southeast Asia War, and we still use anti-radiation missiles today. And we see the two primary anti-radiation missiles used during the Southeast Asia War. On the right-hand side is a Shrike, an AGM-45, and this detected the signals from a surface-to-air missile site from the control vans, but unfortunately it had shorter range than an SA-2 and also didn't have a memory. So the North Vietnamese operators learned to just shut down their radars when these were launched. On the inboard pylon is something called a standard missile. Very capable missile. Actually had longer range than the SA-2, and it had a memory. So the North Vietnamese operators couldn't shut down their van. It didn't do them any good. Now, the Air Force's labs continue to develop anti-radiation missiles today. The Southeast Asia War saw the employment of several different types of precision-guided munitions, including these bullpups and television-guided weapons like the GBU-8 and the AGM-62 Walleye. But most importantly, the Southeast Asia War saw the revolutionary development of the laser-guided bomb. Now, the laser-guided bomb really is a great example of multiple technologies leading to new and transformational capabilities. There's no laser-guided bomb without the laser. And the Air Force Office of Scientific Research had a very important part in the development of the laser by funding Dr. Charles Towns, who developed a predecessor to the laser called the Maser. And this led directly to the first laser in 1960. Now, the development of the laser-guided bomb was the result of the efforts of Colonel Joseph Davis And he was looking for different types of technology that would help our warfighters in Southeast Asia. And he learned of an Army program using a laser to guide an anti-tank missile. Now that program really ended up going nowhere, but he understood that should this technology be applied to a bomb, that could make a huge difference with our warfighters in Southeast Asia. Now the laser-guided bomb basically works by, there's a seeker that's in the nose, and a target is painted with laser energy, and this seeker in the nose translates signals to controls in the bomb and guide it into the target. Now the average circular error probability, or basically on average how far a bomb missed in Southeast Asia using dumb bombs, was about 400 feet. But the advent of the laser-guided bomb reduced this down to 20 feet, which had a huge impact on effectiveness and survivability for our air crews in Southeast Asia. Now, behind me is an F-111, and there are several technologies in the F-111 that the labs worked on. Probably the most obvious one is the swing wing. So there's a pivot point on the inboard of the wings on the F-111, and at low speeds, say on takeoff or on landing, those wings were swept forward, which provided more lift. However, at high speeds, the wings would be swept back, allowing it to fly faster and more efficiently at higher speeds. Now we're going to see a little bit later in the tour just where this technology started with. The F-111 was also the first tactical fighter to have a turbofan engine. And basically a turbofan engine has two streams of air, whereas the earlier turbojets just had one stream. And turbofans basically have higher fuel efficiency than a turbojet. And once we started putting turbofans in our fighters, we see them in following aircraft like the F-16 and F-15. Another feature that the labs worked on are these intakes for the F-111. Now, it's pretty tricky, the airflow that's coming into an intake, because aircraft are have different angles, high angles of attack, different speeds, and so on. And controlling the airflow that's going to the turbofan engine can be very, very difficult. And there were lots of challenges with the F-111. And that type of work is being done today by our aerospace systems.